Okay, good day. So we proceed to our new topic. So this is for rotational motion. So rotational motion refers to motion of objects about a fixed axis. It is also called angular motion or circular motion. So for example, we have a body that is following a circular motion. So what are the properties of its motion? So we have the following. So we are using the symbol omega to represent the angular velocity. So angular velocity will have possible units. This is the RPS, or that is the radian per second or radians per second. The other one is the RPM. This is the revolutions per minute. So for example, that we have a constant acceleration, or let's say we have a constant angular acceleration. Okay, what will be our key equations? So if we are to recall from the kinematics before, so we have that is the final velocity squared equal to initial velocity squared plus 2as, and then we have final velocity is equal to initial velocity plus acceleration times time. Then we have the displacement is equal to initial velocity time plus 1/2 AT squared. So this is for a motion in a straight line. So this time all we have to do is replace the equivalents of these variables, okay, in a circular motion. So again, we have, when it comes to angular velocity, we have the omega. When it comes to angular acceleration, this is the alpha. And then when it comes to angular displacement, this is the theta. Okay, so all you have to do is replace what is our final velocity. So we should write, okay, final angular velocity squared if it is a circular motion equal to initial equal to, we have the initial angular velocity squared plus 2 times the angular acceleration times the displacement theta. So this will be the equivalent equation if it is a circular motion. Then we have, for the second equation, this is the final angular velocity equal to initial angular velocity plus alpha, which is the angular acceleration times the time. And for the last equation or the third equation, again, this is for constant angular acceleration problems. So we have S is theta, that is our angular displacement, is equal to initial angular velocity times the time, then plus 1/2 angular acceleration times the time squared. So again, these are the equivalent equations, okay, when it comes to circular motion. So let's have an example. So for example, okay, we have a room fan is switched from medium to high speed. So the blades accelerate at 1.5 radians per second squared for 1.5 seconds. Determine the final angular speed of the blade in RPS, that is the radians per second, if the initial angular speed of the fan is 3 radians per second. Okay, so let us write first the given. So angular acceleration is given. This is 1.5 radians per second squared. So that is, we have 1.5 radians per second squared. So the time is also given, that is 1.5 seconds. And then we are required to determine the final angular speed of the blade in radian per second. So if we have an initial angular velocity is equal to the 3 radians per second. So among the three equations, okay, what is the most suitable one? Alright, that will be the second one. Alright, so we are using equation number 2. So for equation number 2, this is the final angular velocity is equal to the initial angular velocity plus the angular acceleration times the time. Okay, correction, we don't have squared. Okay, that is the final angular velocity is equal to initial angular velocity plus the angular acceleration times the time. So we have the final angular velocity should be equal to initial, we have that as 3 plus angular acceleration is 1.5, then the time is also 1.5. We have the final angular velocity will be equal to, okay, that is 3 plus 1.5 multiplied by 1.5. So this is equal to 5.25. That is 5.25 radians per second. So this will be our answer for this simple example, our very first example. Okay, so let's have another example. So second example, a merry-go-round has an angular acceleration of 0.35 radians per second squared. At what angle does the merry-go-round rotate after acceleration from rest for 3 seconds? So let us write down the given. So alpha is given. We have 0.35. That is radian per second squared. So according to the problem, so the merry-go-round is starting from rest. So our initial angular velocity will be 0. So for a given time interval of 3 seconds. So we are to solve for the angle of rotation of the merry-go-round starting from rest. So therefore, we are to use the third equation, that is theta equal to initial angular velocity times the time, then plus we have 1/2 angular acceleration times the time squared. So again, that is our third equation. So this is by direct substitution. We have the angle of rotation, theta is equal to, starting from rest is 0, the time is 3, then plus we have 1/2, this is 0.35, then multiplied by the time, 3 squared. So, alright, computing for theta is equal to, okay, that is 1/2, 0.5 of 0.35, then multiplied by 3 squared. Okay, we have that as 1.575 radians. Yes, so we have 1.575 radians. So that will be the angle of rotation of the merry-go-round for 3 seconds, starting from rest. Okay, so let's have another example. Okay, so let us solve our third example. An average car tire has a radius of 0.35 meter. If the car accelerates in a straight line at 3.5 meter per second, calculate the angular acceleration of the front passenger. So for an object that is rotating, for example, for this example, we have a wheel or the tire of a car. Okay, then it has an acceleration along a straight line. So the equivalent straight line motion of due to the rotation of the tires, an acceleration equal to 3.15 meters per second is the same as meters per second squared. So we call this one as the tangential acceleration. So what is the equivalent of tangential acceleration? Okay, so this is the equivalent acceleration along a straight line, okay, due to the rotation of the tires. We have the alpha, again, that is the angular acceleration. So what is the relation of the two? The tangential acceleration is basically equal to the angular acceleration multiplied by the radius. So according to this problem, the radius of the tire is equal to 0.35 met 0.35 meter. So how do we compute for the angular acceleration? We have that as alpha, that is the tangential acceleration divided by the radius of the tire. Okay, so we are now to substitute. What is our linear acceleration or the tangential acceleration? This is 3.15 meters per second squared. This is to be divided by the radius is 0.35 meter. So if we are to observe the unit or units, this is meter per meter second squared. But for rotational motion, the meter per meter is the same as unitless or the same as the radians. So this is an angular acceleration. It should be in radians per second squared. So what is 3.15? We have 3.15 divided by 0.35. Okay, exactly 9. So our answer for this example should be 9 radians per second squared. Alright, this will be our solution for the, this is already the third example. Alright, so we proceed now to our next example. Okay, so this is our fourth example. An electric motor is turned off and its angular velocity decreases uniformly from 1000 RPM to 400 RPM in 5 seconds. So these are the given. Our initial angular velocity is the 1000 RPM, means this is the revolutions per minute. If we are to convert this one to radians per second, we have, okay, what is the equivalent of, one revolution is basically 2 pi radians. And then multiplied by, we have 1 minute is equal to the 60 seconds. So if you are to do unit analysis, canceling revolutions and canceling a minute, okay, the equivalent units remaining will be simply the radians per second. So what is the equivalent of our initial angular velocity? That is simply 1000, okay, multiplied by 2 pi and then divided by 60. 100. So that is 100 of pi divided by 3 radians per second. Then after 5 seconds, our final angular velocity now is 400 revolutions per minute. If we are to observe, our multiplier is simply 2 pi divided by 60. That is from RPM to radian per second, the RPS. But we can still reduce the 2 pi over 60. So what is 2 over 60? That is basically 1, or simply the pi divided by 30. So if you are to convert revolutions per minute to RPS, just multiply pi over 30. So that will give us 400 divided by 30, that is 40 of pi divided by 3. Now in the RPS, the radians per second. And also, the given time is 5 seconds. So these are the given for this problem. Okay, so we proceed to the questions. So for letter A, find the angular acceleration of the motor. So we may use the second equation. That is the final angular velocity equal to the initial angular velocity plus the angular acceleration multiplied by time. So this is the required for letter A. So if we are to substitute, our final angular velocity is 40 pi divided by 3. We have our initial is 100 of pi divided by 3 plus our alpha, then multiplied by the time 5 seconds. So alpha should be equal to, okay, so what is 40 of pi, okay, divided by 3, okay, less 100 of pi, also divided by 3. That is negative 20 pi, then divided by 5 is negative 4 pi. So the acceleration, or deceleration, since this is negative, we have negative 4 pi radians per second squared. So this is our answer for the first requirement. So letter A should be negative 4 pi radians per second. So what about the second requirement? We have that as letter B. Okay, so for letter B, find the number of revolutions of the motor made in the 5-second interval. So what equation will be suitable for this one? I will be using, for question letter B, we'll be using the third equation. This is theta is equal to the initial angular velocity times the time, and then plus we have 1/2 angular acceleration times the time squared. So we have theta is equal to, what is our initial angular velocity? That is 100. Okay, we have that as, this is 100 of pi divided by 3 for a period of 5 seconds. And then plus, this is 1/2. Take note, this is a deceleration, so this should be negative. We have negative 4 pi multiplied by the time, that is 5 squared. So this should be the value of theta. But again, if you are to observe the units, this is in terms of the radians. Okay, so let us compute. Okay, we have 100 of shift pi. This is divided by 3 and then multiplied by 5. Okay, minus 0.5 or 1/2 of 4 pi multiplied by 5 squared. So we have this as 350 over 3 pi. So we have 350 of pi, okay, divided by 3 radians. But if you are to go back with question letter B, it should be in terms of revolutions. So all we have to do is just convert. This is to be multiplied by the equivalent of 1 revolution is simply 2 pi radians. So this should be equal to, so this value will be divided by 2 pi. We have that as 175.3. Okay, we can answer it in terms of fraction. We have 175 over 3 revolutions. So this should be our answer for item B. Okay, so these are our problems, sample problems for rotational motion. 100% kinematics, no force involved. So later on our next discussion, we are to involve maybe forces in rotational motion.